Swayam Prabha. Digital India. Educated India.
Hello, good morning. So, welcome to the course on comprehensive view of speech processing, and today's lecture is 40 in series, and this is the last lecture of this course. And in this course we are going to discuss the another two important speech tasks. So, they are like language identification and speech enhancement. And so far we discussed about the four important speech tasks, that is speech coding, speech recognition, speaker recognition and speech synthesis. And now we are going to discuss the two more speech tasks. One of them is the language identification, the other one is the speech enhancement. And for all these speech systems, development of speech systems are like discussion on speech systems. So, the contents you can able to find from this book. It is an handbook on speech processing. Actually, this is the collected volume, that is like a chapters were collected from the different experts in from the speech researchers. And so, this is the handbook on speech processing, and each system whatever we have discussed. So, there are like multiple chapters were given from this textbook. So, if you want to carry out a research in a speech processing related to any of the tasks whatever we had discussed, so this book will be useful to provide the state of the art till like at least up to 2010. Like later on this deep neural networks and end-to-end systems have been arrived, but this textbook will cover up to like 2007 or 8. And the discussions whatever we are carrying out mostly from this textbook, and there are other related ones. And here, before going to the details of language identification system, first we will see what are the applications that are based on the language identification. We will mention a few of them. The first one is the pre-processing for various speech tasks. So, it means, for example, if you want to perform suppose you want to perform a speech recognition, for example, and so a priori we do not know that what that speech associated to, like which language it is associated to. So, in that case, if you use the like first of all at the front end, if you use the language identification module, so that language identification module will detect or will determine the language that is associated to speech. Then we can able to guide the feature vectors or the speech signal to the appropriate speech recognition system corresponds to that particular language. So, the same way you can also do with the other systems as well, developing the other systems as well. And language, as I mentioned in the very introductory class itself we have discussed. So, whenever we say the speech, discussion with the speech means always associated with the language, and you need to like understand the difference between the speech and audio. So, basically the speech means actually whatever is produced from the vocal tract, and that too associated with the language. It is not that whatever produced from the vocal tract cannot be called as speech. So, it should be associated to some language or language constraints, right, then only you can call it as a speech. Whereas audio means whatever we can perceive through our auditory system, that entire thing can be viewed as audio. It may be speech, music or any other sounds. And the first very important application is that to perform various speech tasks, or basically if you want to interact with a machine. So, first of all this can be used as a pre-processing task in view of machines. First of all, whatever the speech that is arrived, so it will be analyzed which language that particular speech belongs to, then appropriate based on the task, then the appropriate the speech models will be provided for verification and so on. So, that way the language specific speech recognition task where the language identification is required, and similarly for language translation systems, or we can view the speech to speech translation, where in the multilingual country like India, where if you want to have a dialogue with the people from other states who belongs to the other language, in that case if we have a speech to speech translation system where you can very seamless way or very flexible way you can able to speak to them and you can able to carry out the business. right. So, in that case where first of all the first task is that we need to find out what the source language, what the target language, and based on that the speech recognition and other tasks will be performed. And the another application is like a multilingual voice control information retrieval system. This is also like where the information is available in the multilingual form. So, in that case it is required to have like a language identification, and with that we can able to segregate and we can able to perform the proper organization of a data in the context of the languages, and afterwards it will be easier for retrieval also. And similarly, in case of customer care applications also, where a person is calling to the customer care, and based on the customer's language or customer's like location, so the call will be routed to the corresponding human operator who knows that particular language. And similarly, likewise we have like various multilingual applications. In all of them the LID is very much required as a front end to determine the language of a given speech, then afterwards further it will be processed based on the task involved. And coming to the language specific features that are associated to speech, as of now, so far various tasks we have seen like a speaker recognition, speech recognition and so on. But for all of them, if you look at the input that is given to a system is a speech signal, but the tasks that need to be performed are different. In case of speech recognition, the task will be like to determine the sound units. In case of speaker recognition, the task will be from a speech signal you need to determine the who has spoken that. In case of language identification task, the task is that from the given speech signal we need to find out what language that particular speech associated with. So, since as we know that the speech carries the multiple information, multiple types of information, like one is the message, then the speaker characteristics, language characteristics, and the background environment. So, several and then the mood of the speaker, the emotional status of the speaker, all the information is present, and then we have to cleverly use the appropriate information for a specific task. And for a language specific features, if you try to analyze from the speech, they are available at a frame level. It is nothing but the spectral features that are present, the spectral features for which you can able to extract the frame level information related to the language. Then the syllable level information, where here both the spectral information as well as the prosodic features can be exploited. In case of multi-syllable, where basically the prosodic characteristics and the phonotactics. So, it means that the syllable means consists of what are the sound units it consists of, like with the words means what syllables that constitutes a word, and a phrase means what sequence of words that constitutes the phrase. So, all these details can be analyzed using the phonotactics that are associated with the language. And similarly, the positional features also, like the different sound units based on their positions or based on their context also provides the specific language constraints. And so, the language specific aspects of a speech, that means acoustic phonetics means here as we know that each language contains some set of sound units. So, but the sound units based on its context, that is offered by different languages, the characteristics of sound units will be different in the different languages. No, I am not saying the characteristic of sound unit, if you analyze the vocal tract shapes, the sequence of vocal tract shapes for the same sound unit in the different languages, it will be different because of the constraints that is offered by the language are based on the sequence of the phonemes that are allowed by the particular language. So, that way the articulatory configuration of vocal tract for different sound units. And then the phonotactics, that means the rules governing the different phonemes are combined to form a subwords in a different languages. That is known. That is basically the language constraint or the language policy, because there are certain words that are valid in a language. Based on that, there is only some legal sequence of sound units are permissible. Similarly, the prosody, as we have seen that the prosody will play an important role in a language. So, based on the prosody, one can able to discriminate the languages also. And vocabulary and lexical structure. So, this is more towards the language, like what words is consist of, what are the root words, and what are the sequence of words that are valid for a particular language. So, all these are like language specific aspects with respect to the speech. And we have seen this is the one what we already discussed, the implicit LID features, that means language identification. The features that are used will be at a frame level, syllable level and multi-syllable level. If you look at here, the frame level means if you process the speech at a segment level like about 20 to 30 milliseconds range, where we can able to observe certain characteristics that are associated to the language, where the syllable level means if you analyze or if you examine the entire syllable, you can see certain patterns that are specific to a language, and multi-syllable means much broader level. If you try to analyze at a word level or phrase level, you can see some details related to specific to a language. And the issues in a language identification are like they are like generic issues which we come across even for the other recognition systems also, like a variability of speaker characteristics. That means the different speakers may speak the same language, but in view of that, if you look at those speech signals, so from language perspective the speech signals should be similar, but as the different speakers are involved, so therefore the characteristics of the speech signals are different. So in view of that, how do we provide a language identification in a robust way? And similarly, variability in accents, that means same language will be spoken in a wide range of geographical area, and at different parts of geographical areas people will speak the same language but with a different accents. So in that case also the language identification system should perform the LID task very effectively. And variability in environment and channel characteristics, so this is the generic one across all the speech systems. And extraction and representation of a speech specific prosody. So it means that, for example, for a language you can say that there is some rhythm associated to the language. That means when you are speaking, the rhythmic structure that is associated to the language will be unique. Similarly, the melody of a language, that is also, but these two we can able to perceive as a human, but it is very difficult to like articulate and difficult to extract that from a signal to analyze from a machine perspective. And these are the like different cues, like speaker specific and language specific cues that are manifested in the signal and at the text level. So if you look at the language, so these two cues like a prosody and acoustic phonetics, so these you can able to acquire from the signal, and whereas the other ones like phonotactics, vocabulary, language, lexical structure, these things you can able to analyze from the text. So similarly in case of a speaker also. And so these are the like as we have mentioned, these are the various language specific information that is present in speech, like acoustic phonetics level, prosody level, phonotactics, vocabulary and lexical structure. So for these, the features that are derived in view of these cues are like in the acoustic phonetics means the spectral features that are basically derived from the segmental level, and that can be used for language identification. Prosody means, as we see, know that the intonation, duration patterns and intensity patterns. So the corresponding features related to that, duration, F naught and amplitude of the signal, that basically implies those prosodic aspects. Similarly, the phonotactics means the sequence of subword units. Suppose a word contains what are the various sound units it consists of. So based on that, the way the pronunciation of a particular word and the sound units that constitutes a particular word, based on that one can able to like identify or discriminate the languages. And similarly, there is a slightly broader level, vocabulary and lexical structure. That means the way the word sequences are legal in the case of different languages. So all these things can be used for performing a language identification task. And so this is the block diagram, or like a system that is used to perform a language identification task based on the phone recognizer. That means using acoustic processing, nothing but here is nothing but a speech recognition system that gives you the sequence of features, and from that the phonemes will be recognized. It is nothing but your speech recognition system, and it provides the sequence of phonemes, and these sequence of phonemes are given to the different language models, n-gram models, right. We have seen n-gram model is nothing but the just tries to analyze that the possibility of the sequence of words that are like eligible or legal to a particular language. So it means that whatever the sequence of phonemes that are arrived, so they will be fed to the different languages based on the n-gram models, and each model will give you the probability. So based on that, whichever gives the maximum likelihood, that will be hypothesized, and that way that particular language will be hypothesized for the given speech sample, right. This is just similar to the way, the normal way of performing a recognition task for any of the speech task. And here there are various types of models can be used, either the neural network models, support vector machines, or like a CART models, or like even the deep neural networks. So, there are different types of classification, the models, the machine learning techniques can be used. And here in this context, just I mentioned the different types of neural networks, different structures of neural network. One is the AANN, that is auto associative neural network model, this one, and this is the multi-layer feed forward neural network model, and both of them can be used for the classification purpose. And here first we will start with try to see that language identification using a frame level features. So, when you are using frame level features, here we are using these three different types of information that is extracted from the speech signal. So, that is the spectral features, that those are at frame level we can able to extract, and then LP residual means this is the excitation source information. So, here if you look at here these three features, and in that the spectral features corresponds to the vocal tract component, or the characteristics of vocal tract will be reflected more effectively in the spectral features, whereas the excitation source component will be captured, or the information related to that will be the mostly captured through the LP residual and phase of the LP residual. So, we are using these three different types of features, and will build the systems accordingly, will build the separate systems, LID systems with each of these features, and then we will try to combine these evidences, and then finally we will make a decision about the language, what the language identification can be done. And here these features, they may give you a complementary evidences. So, therefore, if you cleverly add the evidences from these three features, we can able to improve the performance also. And here the features that are whatever I have mentioned over here. So, this is the segment of a speech, and then if you apply the LP analysis, you can get the linear prediction residual or excitation signal will be this one, the second plot here. And then upon this excitation signal, like if you apply the Hilbert envelope, you can see that the Hilbert envelope of the LP residual will be like this. Hilbert envelope is nothing but you can see in the Hilbert envelope we have the samples, or the signal will be only in the positive side, whereas the LP residual, it has a fluctuations both at positive and negative amplitudes. But if you apply Hilbert envelope, the signal will become the positive signal, and here you can able to clearly notice that there are peaks at regular intervals. That means that the given speech segment is a voiced segment. And then here you can, the bottom one is the phase of the LP residual. So, here we are using this the LP residual signal, and the phase of the LP residual signal will be used as a features for building the speech language identification task. And you can see this block diagram, the top one corresponds to the building the model with respect to the spectral features. And so, for that, suppose this is the way, this is a standard way of for any recognition system, first of all, from the speech signal, the silences are not important. So, therefore, the silence can be removed, because they will not provide any specific information or any speech related information. So, there is no point in processing the silence. So, you have to remove the silence. Then the differencing is nothing but it's a kind of pre-processing task, where the high frequency components will be emphasized, and then the feature extraction will be done by using one of the techniques, like here we are using weighted linear prediction capsule coefficients, and then afterwards the capsule mean subtraction will be carried out. Then finally, we model using the ANN models, auto associative neural network models. And here this is the case where we just build the model for, we are developed the LID task for 4 languages, Hindi, Kannada, Tamil and Telugu. And here the speech, from the speech the features are extracted, and they are given to these models. Now, we take the evidences, and the decision logic will make a decision about that. And here, since we are considered the features from the 3 different perspectives, that is from a vocal tract perspective, that is the spectral features, and from the excitation, we have considered the 2 different features. One is the excitation source features, and the other one is the phase of the excitation. So, we build the 3 models for each language. So, and from the 3 models we will take a confidence scores and then we will sum up them, and then it will be used for finally making a decision. So, instead of taking the individual components, if we take all 3 and combined in a proper way, the performance will be improved, because these 3 features, they are derived from the different components. So, you will get the complementary evidences, like for certain features are more discriminable for certain languages. So, that way if you add them in an appropriate way, then the performance will be improved compared to the like features from a single component. And now we will see the ones whatever we discussed so far are the frame level features for language identification. Now we will see the syllabic features from the for the language identification task. So, the syllable means, as we know that the syllable constitutes multiple sound units, where in that the vowel has to be there. Vowel is the nucleus of a syllable, and consonants may and may not be associated. Suppose this is a syllable corresponds to like the syllable corresponds to ka, where here this portion is the consonant segment and this is the vowel segment a. And here in the but here we will just consider the CV units, because when you are performing language identification task for Indian languages, instead of considering all possible syllables, just we consider the syllables having structure with CV. So, it means that most of the syllables will fall under this category, like majority of them. So, therefore, we will consider the CV as the syllable here, and for that CV to extract the features. So, here in the syllable, the vowel onset point is a very crucial event in the syllable, and from here the vowel starts, and from this side you have a consonant part will be there. So, therefore, to capture the syllable characteristics, will once you detect the vowel onset point, and then the information that is around the vowel onset point will be used for extracting the features. It means that to the left of this will be the consonant portion, and to the right of this will be the vowel region. So, we will consider some 20-30 milliseconds prior to the vowel and vowel onset point, and then some around from 40-50 milliseconds like after the vowel onset point will be considered for the analysis of for extracting the features. So, therefore, to derive the features here, the vowel onset point has to be detected, and the region around the vowel onset point will be used for extracting the features. And here for detecting the vowel onset points, here we are using the we will extract the LP residual signal, then Hilbert envelope of LP residual signal is considered, and from that here you can able to see that the strength of excitation, where for consonants it is very less, and at the beginning of vowel we have sudden rise in the strength. So, this is an evidence where with which we can able to detect the vowel onset points. So, these techniques have been used, and with which, suppose this is an utterance, and here the markers here whatever is there, these are the vowel onset points for a original or ground truth, and by applying these computing LP residual, Hilbert envelope of LP residual, and for applying some signal processing techniques, here you can see the plot D corresponds to the vowel onset point markers that is provided by the algorithm or a signal processing method, and a ground truth is this one. So, if you look at here these two, like majority cases the ground truth matched with the vowel onset points that are derived by the signal processing method. So, that way once the vowel onset points are available, then we can able to mark the syllabic region, from that the features will be extracted. And this is the same way whatever we have done earlier. Once the syllables are identified, syllable VOP is detected, then the features from the syllable can be extracted and can be used for language identification task. Then the next stage will be like using the multi-syllabic features, because as we seen the language identification, language cues or language specific cues are present at a frame level, that means at a very shorter segments, then at a syllable level and at a multi-syllable level. So, in case of multi-syllable level, if you analyze, so these are the features that are present at a multi-syllabic level, that is the phonotactics. It means that the sequence of sounds or sequence of words, so that those are indicating the phonotactics. And a broad phonotactics means here, instead of using the sound units as it is, we will group the sound units based on the place of articulation and manner of articulation at a broader groups, and we used to indicate the group information instead of the specific syllable specific information. So, that way the broader phonotactics indicate the the sound units with respect to the specific production mechanism. And the prosodic features, as we are already aware of, that kinds of intonation patterns, duration and energy patterns, and then combination of these two like phonotactics plus prosodic features. So, that way here we can able to build the systems using phonotactics alone and using prosodic features alone and a combination of that. So, these are the features that are extracted with respect to like using phonotactics and prosodic features. You can see for phonotactics means for syllable identity, that is we indicate the 4 parameters, because the syllable can be defined as C power m v c power n, that we have seen in the last class, where v is must and the consonants may and may not be present. So, here we consider that the 4 segments that constitutes a syllable, it means 1 vowel segment and 3 consonants may. Suppose if the syllable contains only the 2 segments, then the other segments will be considered as a null. So, that way we can able to parameterize the syllable identity, right. And suppose if you consider the trisyllabic, the multisyllabic, so the number of features that will be in view of phonotactics will be 12. If it is a single syllable, that is a 4 features or 4 parameters, and if it is a trisyllabic, then there are 3 syllables, so 3 into 4, 12. Likewise, the broad phonotactics also the same way. And coming to the prosody, the syllabic structure, as I mentioned here, it means that where the vowel is present and vowel is at the beginning or vowel is at the middle or last. So, that will be indicated by syllabic structure. And again intonation is indicated by again the 3 values, 3 f naught values, because the entire intonation pattern of a syllable can be viewed as at the beginning what is the f naught value, middle and at the end. Similarly, the duration and the positional information also. So, this way the prosodic information will be indicated for a syllable, and here these are the 4 parameters that are used to indicate the phonotactics for a syllable. And now, in case of trisyllabic, then these are multiplied by the corresponding number of syllables. So, that way if you use the multisyllabic case, the prosodic features are indicated by 27 dimensional vector, and then the phonotactics, that is a 12 dimension. So, therefore, if you add 12 and 27, it becomes, in case of phonotactics plus prosody, the number of features will be 39. And so, these are the neural network models that are used for developing the LAD systems. In view of phonotactic features, we have like preceding syllable, present syllable and following syllable, right. So, the 3 syllables and each syllable consists of 4 features. So, the 12 features will be fed as input and the corresponding language identification will be provided. So, with that the system, the multi-layer feed-forward neural network model can able to discriminate the languages. And whereas here the same system here, but here the input will be 39 dimensional vector, where the 12 dimensions corresponds to the phonotactic features and the remaining 27 dimensions corresponds to the prosodic features, whatever we discussed from the previous table. So, this is the input and the corresponding language IDs has been given as output, with which the model will be trained and with which the model will be developed, the system will be developed. And all these things whatever we have discussed so far, we have a labeled data. Suppose if the data is not labeled, that means suppose just raw speech signals are available for us without any labels or without any annotation. In that case, how do we perform that? How do we extract the prosodic features? So, these are the prosodic features that are used, like these are the things which we have seen in case of speaker recognition also. Like with respect to intonation, it is parameterized using the 4 features like amplitude tilt, duration tilt and the change in f naught and other one. Like rhythm means the syllable duration and the duration of voice region. Stress means that means change in the log energy in the voice region. So, these are the 7 parameters that are used to indicate the prosodic features, and we will see that how do you extract those features. So, if you look at this, is suppose this is the speech utterance corresponds to some sentence, and here this is the intonation contour, nothing but f naught contour. If you look at, suppose somehow if you identify if you detect the vowel onset points, so between the vowel onset point means it is nothing but a syllable. So, you can see that in each syllable, like the pattern, the f naught contour or intonation pattern takes a different shapes, that means it has a very dynamic characteristics. So, at some places it is rising, then followed by falling and then rising, and here you can say it is a flat and then afterwards falling down. Likewise, if you look at here in each syllable, it follows the different dynamics that are involved. So, to capture this one, you can use the tilt model to capture these dynamics of intonation patterns associated to syllables. will make use of the tilt model, which we had discussed in the previous lecture. So, for doing that, here the overall block diagram to capture the f naught features will be like from a speech signal we will extract the f naught, and then we will smooth the f naught contour, and we will extract the VOPs, vowel onset points, which used to provide the syllable boundaries, and then with respect we will associate this f naught contour with respect to the VOPs, that means with which you can get the intonation patterns that are associated with respect to syllable. Then afterwards, using a tilt model, we can able to derive the features. So, this one, if you look at, if you remember this, the same slide we have been used for even for speech recognition also to model the speaker models for in view of intonation patterns. So, here if you look at here, this is a generic pattern of rise followed by falling. So, here you can see this is the rise duration, this is the fall duration, this was the rise amplitude, and this is the fall amplitude, and by using this we can able to derive the amplitude tilt and duration tilt. And there are other parameters also you can able to see from this change in f naught and other things, right. So, once then if you look at this particular slide, you can see that the possible patterns, intonation patterns, styles of intonation patterns, either it is like falling or rising, like a rise followed by falling, right. So, there are different types where with having different durations, and you can able to model them or you can able to represent them with respect to appropriate tilt parameters, amplitude and duration tilts. And so, this is here by using the Hilbert envelope of residual, you can able to mark the voiced regions in the speech signal. This is a speech signal, and here you can able to mark the voiced region by using a signal processing technique what we have already mentioned. That means, here if you detect if you determine the LP residual, and afterwards if you compute the Hilbert envelope of that, and then based on that you can able to compute, here you can see that the higher portions corresponds to the voiced regions and the low amplitude regions corresponds to the unvoiced. So, therefore, by using that you can able to derive the voiced unvoiced decision, and then with that you can able to find out the other parameters like rhythmic parameters and stress parameters also. So, once we have those parameters set, then we can able to build the model without any labels at all. Then coming to the next the application or the next speech task that we are going to discuss here is the speech enhancement. And here in the speech enhancement, the objective is to like from the name itself, we will try to enhance the speech, right. So, it means we need to improve the quality of the speech, and here improving the quality means there are different perspectives. Suppose the improving the quality with respect to the human listener, that is known to be the perceptual aspects, and other one is that suppose we have a speech system that is developed with a clean speech, and somehow the speech sample that is used to validate or used to like perform a classification, perform some identification or recognition task, where the speech samples that are acquired from the different background environment, for example, so or like a noisy environment. So, in that case, if you try to determine, if you try to recognize, perform the recognition task, the performance will be very poor because of mismatch, because the models were built with a clean speech, and when you are testing the models with a noisy speech, the features will be different, features will be noisy, and when you try to perform the recognition task, the performance will go down, will miserably fail. So, therefore, in that context where we need to perform a feature compensation, or we need to somehow like map the noisy features to the clean features, so that the recognition task will not be affected at all. So, that way in case of speech enhancement, like from the human listener perspective, the speech enhancement will be like the auditory quality or a quality of a speech that has to be enhanced, so that the humans will feel more comfortable and appreciate the quality of a speech. And the other one is that like from a system point of view or from a machine perspective, based on the task, we need to retain or we need to ensure that the performance of the system should not be like disrupted because of the noise that is added to the speech signals and all. And first of all, before going to those details, first of all let us see that, so why the speech becomes a noisy speech, like what are the various occasions or various sources of noise, so that will correct the speech signal. And here these are the possible sources of noise you can see here. Suppose if you capture a speech signal from a close talking microphone, then the speech signal that is just produced will be captured by a microphone, and with that the speech signal strength is very high and the background environment will be like less. So, therefore, the speech will be more pronounced and you can see that it will be more clear and you will feel that it is a very clean speech kind of a thing. Whereas, the same microphone, if you keep some 4 feet or 5 feet away from the speaker and if you try to record that, then the speech that is collected by distant microphone will be noisy. Even though the noise, the background noise is not much, but the moment once you keep a microphone away from the speaker, the speech degradation or like there is a decay in the speech power will happen with respect to distance, right. For every feet there will be certain amount of the power will be decayed and the moment once the microphone is kept at 4 feet or 5 feet away, then the speech that is captured will be very different or will be noisy, because there the same background noise will be there when you keep a close talking or a distant mic, but at a distant mic the speech signal strength will be lowered, very much lowered. So, because of that you feel that the speech is the noisy that is captured by distant microphone. Similarly, the background environment, it means that from where you are collecting the speech. If you are collecting a speech in a very studio environment or an anechoic chamber, then the speech will be very clean, like the attenuation will be very less, the speech will be very clean. Whereas, if you collect the speech from a different environments like in indoor or like outdoor, indoor means you have a walls where the speech signal will be reflected from the walls, and again you have like the effect of reverberation will takes place. Outdoor means the wind effect, or factory means like the other noises will be there. Likewise, based on the background environment, the speech will be corrupted, right. And the recording device also, the device that is used, suppose if you use a high quality microphone, the speech will be different. If you collect the speech from a cell phone, based on the coder that is present in the device, the speech will be quality depends on that. Similarly, the transmission channel, suppose if you collect a speech from a telephonic channel or from telephone speech, it will be different because the telephone channels are band limited. So, therefore, some high frequency components will not be present at all. So, therefore, the quality of a speech will be degraded. Similarly, the reverberation, as I already mentioned, that is the speech signal instead of a direct speech signal, the echoes from the different objects also will be arrived, and with that due to the phase missynchronization, you can able to see the quality will be degraded. Similarly, the interfering speakers. Suppose there are multiple speakers are speaking in a room or in some party environment or some meeting environment. If you capture a speech from a microphone, from a single microphone where multiple speakers are talking, then in that case, the speech appears to be like very noisy, and in that actually the desired speaker speech, if you want to enhance, it means that either you need to emphasize that particular speech or you have to de-emphasize the other speakers. So, that way these are the different possible sources of noise that can be impact or that can corrupt the speech signal. And then as I mentioned, the objectives of speech enhancement, listener's perspective, and in view of developing the speech systems. Listener's perspective means ultimately the human listener is the end subject. So, therefore, he expects to be the intelligible, that means he has to receive the message, and the quality, that means the speech quality should be more natural, and auditory fatigue, that means when you are listening to the speech, if it is a more natural and it is a pleasant, then you can able to, you don't feel any burden or you don't feel any stress or anything, or you can otherwise you can able to appreciate. It means the listening effort that is involved in the listening to speech for a long time. So, going to be auditory fatigue. So, all these things will be considered when you are analyzing the speech enhancement from the listener's perspective. Whereas, from a developing a speech systems perspective, so it means that we know that the speech systems will be built with in some other the speech with a clean speech or whatever, and whereas when you are testing the systems or when you deploy the systems in a practical environment, the speech signals that will be used for validation or for analysis purpose or recognition purpose, they may not match to the speech systems that were built. So, in that case, we need to have some kind of a feature normalization or like a feature compensation has to be taken care. So, that means noisy features to be mapped to a clean features, so that the performance of the systems will not be degraded. Yeah, coming to the applications, there are several applications you can like imagine, like there are several applications which are based on the speech enhancement. Basically, the devices that are using the speech, where in that case the speech enhancement is very much required, right? And because of mobile phones, for example, so where you are listening to the speech from through like from a person conversations from a distant person, so the speech should be enhanced, right? And similarly, the speech generated by noisy environments, so there are also like military applications where in case of battlefield somebody want to communicate to the central station or control station where it's a lot of noise used to be there, but you need to have some speech enhancement techniques where the noise has to be removed. Similarly, aircraft cockpits, lot of engine noise and other noise used to be there. In presence of that, whatever the pilot want to communicate with the ground station, and development of speech systems as we have seen, and perceptual speech enhancement from a human perspective, like you need to have speech enhancement, and then the speech enhancement for parameter normalization, that also we have discussed. So, these are the different occasions where the speech enhancement task is required, carried out. And then when you are evaluating the speech enhancement, there are different ways to evaluate the speech, like objective evaluation. It means that by determining the SNR of a speech signal, one can able to comment on whether the speech is good clean speech or like a noisy speech. Like if the speech SNR is greater than 30 dB, then you can consider that as a clean speech, 30 or 40 dB, more than that. If the speech the SNR is less than that, it indicates that some noise is present in that. Maybe the humans can tolerate, but some cases it is troublesome. And some segmental SNR, instead of using one SNR for the entire speech utterance, because when the speech is corrupted through noise, sometimes the time varying noise will be affecting the speech signal. So, in that case, it is better to have a segmental SNR, which gives you the average SNR, or at each segment what is the SNR that is involved. Like with the PESQ, that is the perceptual enhanced speech quality. So, this is also a measure that is used to like perceptual evaluation speech quality, evaluation for speech quality. So, these are the objective measures with which you can able to analyze the speech enhancement task. And the subjective evaluation is that depending upon the perceptual aspects. It means that suppose if the task for speech enhancement is for a human, then in that case the listening test will be used to check the intelligibility and naturalness. Intelligibility means like from the speech the listener has to like write down the words that he has listened to, that or that he has heard from the speech, enhanced speech, and based on the number of words he has correctly reproduced, based on that the intelligibility will be assessed. Naturalness will be like, it's like based on the, because humans are aware of the normal the human speech, it appears to be more natural. With respect to that, the speech enhanced the enhanced speech from a device or from any system can be compared with that, and then with on a 5-point scale the scores will be given, and taking the average of that, that is nothing but mean opinion score. So, with that also we can able to evaluate the speech enhancement methods or the speech enhancement systems. And then coming to the quality of a speech, it basically in a speech signal, the quality or a naturalness of a speech is basically from the voiced and periodic segments, from the voiced segments and periodic segments. So, if you try to enhance, or from the basically from voiced and periodic segment, both are same to some extent. So, from these segments of speech, they provide the naturalness to the speech, whereas intelligibility is basically due to the consonants. Intelligibility is basically due to consonants. So, that way this is the test we carried out and we discussed at the introduction in the speech processing. Suppose if you in the speech utterance, if you remove all the vowels and if you place only consonants, but still you can able to make out, right. And similarly, suppose if the only vowels are present, then you do not make out. That is from the text perspective. The same thing also observed in the speech signal also. The consonants will play a major role for determining the words, or from perceiving the words or perceiving the message from the speech. And coming to the fricatives, they are more vulnerable, because fricatives means the actual sound itself is observed to be like a kind of a noisy thing, but there is a sound. But if the speech is corrupted, the fricatives are already noisy and a noise is superimposed on that. So, it is more corrupted, and it is very difficult to enhance the fricative portions of a speech. Yeah, these are the various types of noises that are encountered in the context of speech enhancement, like broadband noise, impulsive noise, band limited noise. So, these are nothing but the frequency characteristics of a noise, that depending upon the source of noise, that will be the broadband noise. That means that a much wider band of frequencies are present in this noise. Impulsive noise, it means the noise, it is a temporal effect. The impulse, that means noise is present a very short impact or short instance of time, and band limited noise, only specific band and noise frequencies are present. And the noise may be either steady or time varying. Steady means throughout the speech the same noise structure is observed, and time varying noise means as the speech proceeds, like at a different portions of a speech we have a different types of a noise may be there. Like suppose a person is walking and he is speaking through a mobile phone, and when he is walking, maybe at initially he may be the indoor, and afterwards he may be went outside, then afterwards some car is going adjacent to him. Likewise, at different scenarios where the different noises will be associated to the speech, so it is not to be time varying noise and all. And likewise, the noise strength also can be varied with respect to time. And the techniques for noise removal, that depending upon the noise, how corrupted the speech, like suppose if it is additive noise, then we can able to we can remove the noise, or we can able to enhance the speech by noise subtraction or noise filtering. Because if it is, since it is additive, then by knowing the noise characteristics or noise spectrum, we will estimate the noise spectrum, and then we can subtract from the noisy speech, then the leftover will be the speech spectrum. That was the idea. But when you are removing a noise spectrum from that, there will be some distortions also will be introduced, that is known to be musical noise and all, because even the speech spectrum is also disturbed. So, that leads to some musical noise that will be introduced as an artifact of this noise subtraction or noise filtering. And a multiplicative noise, suppose if the noise added will be multiplicative. So, in that case we can remove the noise by using, first you apply a log. When you apply a log, then the noise component and a speech component will become additive. Then afterwards you can able to subtract. Suppose the noise is convolutive noise, it means that the speech and the noise, they are convolutive in the time domain. So, in that case, if you want to remove a noise, first you apply a frequency domain. So, when you apply a frequency domain, then in the frequency domain this noise and speech spectrum will be multiplied, or a product will be observed. Then on that, if you take a logarithm, then it becomes additive, then you can take a subtraction of a speech spectrum, of a noise spectrum. And there are different enhancement techniques that already we have mentioned. One is spectral subtraction. So, spectral subtraction means here, suppose if we know that the speech is corrupted by noise, and we know that at certain that means during silence regions, that is at the very beginning, or in between the pauses, or in the pauses, or in between the some phrases and all, where there is no speech at all, at that time we can assume that the signal that is only due to the noise. So, if you analyze the noise characteristics, or if you estimate the noise spectrum from these places, from these locations, and then that noise spectrum will be removed from the whole noisy speech. So, that is the idea of the spectral subtraction, and this will introduce some artifacts as I mentioned. And second one is the harmonic filtering, and as I mentioned that in the speech signal, the harmonic components are the periodic structure or harmonic components in the spectral domain. So, they are basically indicating the naturalness to the speech. Suppose if you want to enhance the speech, one way is that from a noisy speech you can separate the harmonic components and you try to emphasize that, or otherwise instead of separating, just if you identify the harmonic regions and try to enhance that, or try to de-emphasize other regions other than harmonics. So, that way you can able to enhance the speech, and that gives you the lot of perceptual enhancement. And parametric resynthesis means from the noisy speech you try to extract the vocal tract parameters and excitation parameters and resynthesize that. So, that way the noise will be come down, the intelligibility will be there, but the speech will be not natural one. And when you are performing these modifications or performing enhancement, you can perform the enhancement either in spectral domain or in the excitation source domain, or in both also. So, but if you perform the enhancement or this modification spectral domain, it is what mean by the spectral subtraction, where that introduce some artifacts, because the samples are very much correlated in the speech signal. So, therefore, whatever the modifications you perform, that leads to some artifacts or some kind of a distortions it will be introduced as part of the noise removal. Whereas, in case of excitation source, the idea is that excitation source itself is like nothing but the error signal in the LP analysis. So, error signal means the samples are random. So, therefore, even though if you do some modifications on the excitation signal, that will not impact, that will not perceive as a distortion much. So, therefore, if you want to perform the speech enhancement from a perceptual aspects or from a auditory perspective, then one can able to like try it out the speech modifications on the excitation source, so that it is not perceivable, right. And another one, perceptual enhancement means one way is that enhance the speech regions and de-emphasize the non-speech regions, like wherever the speech is present, try to enhance that. So, in that case the already the noise is level is lower in the speech regions. So, therefore, the speech will be enhanced. It is basically for a perceptual enhancement. And here we will look at here just for illustration. Here you can see this is a clean speech signal, and if you look at its spectrum, you can see the spectrum is something like that. Here this is this is like a wideband spectrum. You can see that the striations are in the horizontal direction. So, this is a wideband spectrum, and here speech is corrupted by noise, some noise is added at certain level, and in that you can see that the spectrum of a noisy speech will be the same spectrum. On that the impact of a noise, you can see that it is there throughout, and then if you perform some enhancement on that based on the techniques whatever we just mentioned, this becomes the enhanced speech. And on the enhanced speech, if you look at the spectrum for enhanced speech, this is somewhat better than the second one, right. But the first one is the more it is the ideal one, but here the third one is also more close to the first one. So, that way you can able to analyze the speech enhancement through like by human observation or by observing the spectrograms. And here how do we do it? Like, so one way is that, as I mentioned that earlier, so we can able to perform this speech enhancement modifications either in the residual either in the excitation signal or in the spectral or in the vocal tract. But modifying the signal at a vocal tract or at a spectral level where the speech correlations are more, so that will leads to some distortions, that will introduce some artifacts or distortions. So, the better is that excitation signal, and here this is the one where you can able to see that this is the speech signal, and for that if you analyze autocorrelation, you can see that there is a center peak, and afterward the side peaks are not the prominent, right. And if you take the excitation signal, you can see that this is the center peak and then this is the side peak, indicate that this is the periodic signal. But the side peak is there, but it is not very clear, there are other peaks also around that. So, instead of using excitation signal directly, if you use the Hilbert envelope of excitation signal, which gives you only the positive components or positive signal, and if you perform autocorrelation on this, you can see this autocorrelation signal is very clear. You can see the first peak is this one, that is center peak, the next peak is the dominant peak is this one, with which you can able to clearly notice the identify that the speech is a voiced speech. And so, the objective here is that, suppose for example, if you capture a speech signal through a single microphone, it is not to be single channel. Speech captured through single channel means if you capture the speech signal through a single microphone, then whatever the speech that is acquired from a microphone, that may be noisy. Suppose if you collect the speech signal from a distant scenario, so the speech will be the noisy speech, and the scenario is known to be the speech that is captured through single channel, only one microphone, right. And that is the case, that is the most of the times that's what happens. We have only one microphone, and with that we need to carry out various speech tasks. We need to acquire the speech signal and we need to perform certain speech tasks. And the most of the existing methods, what they do, they try to estimate the noise spectrum by analyzing the beginning portions where the speech is not present, and then after estimate the noise spectrum, then the noise spectrum will be subtracted from the noisy speech, and with that you can enhance the speech. That was the idea. But as I mentioned that that leads to introduce some artifacts, And second one is that estimation of degradation is also very difficult, because the noise itself is a random. So, estimation of its noise spectrum, or you can say this probability density function, is highly difficult. And that too in case of time varying noise, where the noise spectrum is varied with respect to time, right, where the SNR may be varied or the type of noise may be varied. So, therefore, it is difficult to do that. Instead, our proposed the other way is that actually instead of bothering about the noise characteristics, try to enhance the speech regions, and then with that whatever the noise it will be there, the speech will be enhanced. And for doing that, here we will just take this is the like highly voiced region of LP residual, and this is LP residual having low voice region, and this is the like non voice region, are kind of a noise. So, if you try to analyze the autocorrelation, you can see that the autocorrelation for like a high voice regions will be like this, autocorrelation for low voice will be like this, and autocorrelation for a noise or like non voice will be like something like this. And here the PS is nothing but actually the center peak to the first peak ratio, the height of a center peak to the first peak ratio, that is indicating the PS, that is the peak to side lobe ratio. So, it is nothing but 0.62 in case of highly voiced regions, and low voiced regions is about 0.24, and in case of noise it is like very low. And we will exploit this characteristic for identifying the speech regions. So, on a noisy speech also, if you perform this kind of autocorrelation, and if you try to compute this peak to side lobe ratio, and if you derive this peak to side lobe for this noisy speech, you can able to find this way. And now, after smoothing this one, you can get this kind of signal, and then from this you can able to derive that actually wherever the peaks are there, it corresponds to the voice signal. So, therefore, you can able to derive from this, you can compute the speech regions and all. And here what we do, after knowing the speech regions, then we will extract the LP residual from this, and the LP residual is weighted by this one. So, weighting by this one means wherever the speech regions are there, the LP residual signal will be protected, and non-speech regions, the LP residual signal will be lowered, the amplitudes will be de-emphasized and all, and use that LP residual to again synthesize the speech, so that the speech quality will be improved. You can see that example to that. Suppose this is the noisy speech, and if you look at the spectrogram, it is something like this. And if you enhance the speech by using a method whatever we have discussed here in this, we will first identify the speech regions, then afterwards the LP residual will be weighted by that, and afterwards we will again synthesize the speech. You can get a speech something like this. This is the time domain, and if you look at this spectrogram, you can see the spectrogram is clean compared to this one. The same thing for some other sentence, if you look at here, the similar thing is observed. And this is the one another scenario where you can see here, this is the speech is corrupted by noise heavily. You can see there, you cannot see a speech waveform at all inside. So, noise is so heavy, and so therefore, you cannot see a speech signal at all. This is the speech is completely immersed in the noise. And if you look at the spectrum also, you can see the spectrogram also complete dark. You do not see any pitch harmonics, nothing. But here also, if you apply the same technique whatever I just mentioned, identifying a speech regions, is nothing but just perform autocorrelation function on the residual of this one, and weighted by that and synthesize back, you can see a speech signal like this nicely. And here you can see this one, and here you can see for this, if you play this enhanced signal, you can see a lot of improvement over that. This is for the single channel case, and you can able to perform a speech enhancement more effectively if you use the multiple microphones instead of having a single channel. Suppose for example, when I am speaking, and suppose there are multiple microphones that are placed in the different locations in a room, and the same speech signal that is captured by these multiple microphones, and then we can use these signals, because these the signals that are captured by different microphones, there are different delays are involved. So, by identifying the delays, and then if you adjust the speech signals and coherently add them, then the speech enhancement will be carried out, because what happens is that the speech signal that is captured by different microphones involves a different delays. So, if you compute the delays, and then if you adjust, or if you can coherently add those speech signals by adjusting the delays, then what happens, the speech regions will be added up. So, with that the speech enhancement will takes place, and whereas the noise is present or non-speech is present, there also some additional takes place, but since it is a noise, so when you add the two noise signals, then the amplitudes will be reduced, and the noise is not emphasized at all. That was the idea in using a multi-channel case. So, in this case actually if you have more and more microphones, then enhancement will be better. So, the idea here is that actually by using the cross correlation, you can able to compute the delay that is involved between the two microphones. And then if you look at here in this case, suppose the speech is captured by 3 microphones, here these 3 plots corresponds to the residual signals that is captured by 3 microphones. And here if you know, by knowing the delays, if you add the 2 microphones like 1 and 3 and the 2 and 3 with appropriate delays, you can see that if you add this all the 3 signals in the coherently by compensating the delays, you can get the signal something like that. You can get a residual signal which is properly emphasized. And if you incoherently add, if you just simply add them, then you can see that the residual signal is something like this. So, therefore, by enhancing, coherently added residual signal will be used to synthesize the speech, and with which you can able to see a lot of enhancement. So, these are the examples of speech, microphone 1, microphone 2, and if you enhance them like by simply by waveform adding itself you can see some enhancement, but if you enhance if you add LP residuals and then further if you synthesize back, you can see the clean speech. The same thing with another example. In case of multi-speaker environment also, we can use, that means the multiple speakers are involved. By using the multiple microphones, you can able to capture the speech from all the speakers with the different delays, and then by compensating the delay, you can able to again perform the enhancement. Here also you can see that there are 2 different speakers like, and the delays that are involved will be like a two because the speaker locations are different. So, therefore, the delays that are involved will be different, and then if you enhance that, you can see that in one case one speaker will be enhanced, in other case the other speaker will be enhanced. So, with which you can able to even separate the speaker tones also. Like you can see here, this is the microphone 1 speech, this is the microphone 2, like where the 2 speakers are involved. By enhancing that one, you can able to see the signal something like this. Like, yeah, this is the end of the lecture. Okay. Thank you.